All right, this is the continuation of the proofs from homework 2. In claim 2, we're proving that if S is compact, then the supremum of S is an element of S. So we start off allowing the reader to give us any compact set. We know that compact means that the set is closed and bounded. So this means, so since S is bounded, I'll just write BDD, bounded. That means the supremum of S exists. And so we'll give it a name. We'll call it beta. So I'm going to refer to this as beta so I don't have to keep writing sup S. That's all that we need the boundedness for, is to know that there is a supremum. And then since S is closed, we know S complement is open. Now, most of you argued for this in terms of limit points, which is fine. I would suggest, unless the statement of the claim is about limit points, then probably arguing with limit points is not really any easier than just using the definition of closed. So I'm going to stick to the definition of closed. But you can make it work. It'll work okay with limit points, but the definition of closed and open, the definition of open is just easier to work with. I don't have to think about deleted neighborhoods and all that stuff. So I know the complement is open. Okay, so that's what I know. And so either the supremum, either this beta is in S or it's not. So let's argue by contradiction. So suppose that beta is not in S. Now, the reason that appeals to me in this proof is because that means that beta is in the complement of S. And so now I'm in a situation where I have an element of the complement of S, and I know that the complement of S is open. So I have a number inside of an open set. And so I know that means that there is a neighborhood. So there is an epsilon greater than 0 such that beta minus epsilon, beta plus epsilon, this interval, is a subset of S complement. And so that means, back in terms of S, that means that beta minus epsilon, beta plus epsilon does not intersect S at all. So there's nothing in common between this neighborhood that I've created of beta and S. All right, so why would that be a contradiction? Well, beta is supposed to be the supremum of S. And so we know from theorem 1.1.3 that two things are true, that beta is greater than or equal to x for all x in S. Okay, so that means that the beta that's in here is actually bigger than everything in S. So when this neighborhood misses S entirely, in particular, the stuff between beta minus epsilon and beta are missing S entirely. And secondly, remember theorem 1.1.3 said that for every epsilon, there's something in S that's between beta and beta minus epsilon. And so that's going to be our contradiction. So there's something in S, this is what the theorem says, there's something in S such that x naught is between excuse me, between beta minus epsilon and beta. So that's because beta is the supremum. So that was our characterization of supremum in terms of epsilons. That's pretty frequently used. The reason we have that characterization in terms of epsilons in theorem 1.1.3 is that it's very similar to our statements about epsilon neighborhoods and so forth. So in this chapter, with limit points and boundaries and whatever, if there's something we're trying to prove about the infimum or supremum, probably theorem 1.1.3 is going to be the characterization of supremum or infimum that allow us to tie it together. So anyway, so that's a contradiction. This x naught is in this neighborhood. So I have so this statement and this statement are contradictory, right? Because the x naught is in S and the x naught is in here. So the x naught is in this intersection, but the double starred statement says the intersection is empty. So this is a contradiction. So that means that beta is in S, right? This was my assumption that led to the contradiction. So that's what I want to prove. All right. I forget how I wrote this up on the solutions. It was probably slightly different than that, but it definitely is going to use this fact to tie things together. You don't have to do it by contradiction, but that fact is going to definitely be in there somewhere. All right, the third claim is about boundaries, and so we definitely want to use the definitions of the boundary points. So if you're not using the definition, if you're just sort of waving your hands at your intuition about what boundary means, that's not really going to be a proof. So you see I've set this up. I'm trying to show a subset structure, and so I've set it up so that I'm asking for any example in the left side set, and so down here I'm going to say thus x naught is in the right side set. That'll be my conclusion. So if I can start from this statement up here and end with this statement, then that proves the subset relationship. So therefore, subset, sorry, the boundary of the union is a subset of the union of the boundaries. So that's how the proof should go. Now, to show that something is in a boundary of S1 or a boundary of S2, what I need to show is that that particular x naught has the property that every neighborhood around the x naught is in the set and also in the complement of the set. Let me say that again. Every neighborhood of x naught has something in the set and also has something in the complement set. Obviously not the same something. That's what I need to do. So it has to be for every neighborhood of x naught, and so that's how my proof should be structured. So I'll say let epsilon greater than 0 be given. This is how I ask for a neighborhood. And consider this neighborhood, I'll just call it N, just for, so I don't keep writing out this stupid thing, x naught plus epsilon. Okay, so in other words, I'm asking for a neighborhood around x naught. Now, because I'm given that x naught is in this boundary, I do know something about this neighborhood. I know that something is in the intersection of N and that set, and something is in the intersection of the neighborhood with the complement of the set. Now, that's pretty bad. Okay, so that's the definition of neighborhood. That a neighborhood, it's the definition of the boundary point. So x naught being in the boundary means that this neighborhood that I've been given, I know intersects both the set and the complement of the set somewhere. It turns out that knowing the names of these somethings is actually useful because we don't have to actually construct too much here. It's really the same somethings. So I'm going to call the something that's in the neighborhood and the union Z, and I'll call the other something, I'll call it Z prime. I think that's consistent with my solutions. But I'm going to give them names. The reason that helps is because this set, this intersection of the union of the complement of the union, is really the same as the intersection of S1 complement intersect S2 complement. So that's De Morgan's laws again, that the union, the complement of the union is the intersection of the complements. And so the reason that's significant is that if you're in the intersection of three sets, then you're also in the intersection of two of the sets. So this Z prime that I'm talking about here is actually in the intersection of N and S1 complement. It's also in the intersection of N and S2 complement. Because it's in the intersection of all three of them, it's in the intersection of the neighborhood with either of these two complements. And that's what I want to know. I want the neighborhoods, I want to know that that there's something in that there's something in the intersection of the neighborhood and the complements of these sets. Okay, so I actually know it's in both of those. And so similarly, this construction in intersect S1 union S2, I'll just write note that the fact that Z is in the here means that Z is in either, can't write on a snow day, S1, or Z is in intersect S2. Okay, if you're in intersect the union, then you're in one of those two things. So what's going to happen is I really have two cases. You can do the old without loss of generality thing here. That's fine. I don't think there's any, there's nothing special about one subscript or the other. But I believe in the solutions I wrote cases just to be thorough. So cases are when you're too chicken to write without loss of generality. So if Z is in here, remember from this statement, Z also is in, man, can't write an intersection sign without one, I could turn into an A. We also know that's because Z prime, we know that Z prime is in the intersection of three sets, so Z prime is in the intersection of two of them. That means that we have something in the intersection of the neighborhood with S1, and we have something in the intersection of the neighborhood with S1 complement. That means that we know that X0 is boundary point of S1. Okay, no matter what neighborhood you give me, there's something in intersect S1 and something in intersect S1 complement. So that means that the something that the neighborhood's around is a boundary point. And case 2 would be similar and would conclude that X0 is in the boundary of S2. So one of those two things has to be true, so therefore X0 is in one of the two boundary sets.